All right, shall we get started? Maybe you guys can talk in the middle. I don't know if this is because of the spring carnival aftermath or the exam aftermath, but we have fewer people today here. Which one do you think it is? Carnival or exam? Probably both. Well, you worked hard and then partied hard and then back to back to the last part of the lectures, hopefully, last part of the class. We'll continue prefetching today. I marked it as 30A, and then hopefully we'll move to multiprocessing as 30B. But you know that you have your homework 6 due today, after the carnival, not on the day of the carnival, which is good. But this you should have done already, hopefully. And your lab is due on Wednesday, and we'll have another lab, and we'll discuss the timeline for that lab, because we don't want it to clash with the last day of classes, because your last exam, final exam is actually 3 days after the last day of classes, which you should start preparing for. But this lab, finish this lab first. Hopefully it should be fun on the memory hierarchy. Is anyone done yet? Nobody? Almost, that's good. But there's only 2 more days left, so actually 3 more days, including today. OK. Feedback, I've gotten through all feedback. I haven't summarized it, but many of you wanted more lectures, even though you know that they're long. Many of you said they're long, but much of the feedback was it is informative, and you would like to learn more. So I will continue the lectures. So this is the plan for the rest of the semester. We'll have 3 lectures this week and 1 next Monday, and 2 wrap-up and recitation sessions next Wednesday and Friday so that you can prepare for the exam as well as do the last lab. Does that sound reasonable? Hopefully you'll learn a lot. Work hard too, but that's what you want also. You guys are a good bunch because you're working hard as well as learning a lot, I think. You got a lot of good feedback. I'll try to go over it when we have time in one of the next lectures. OK, I have an office change. I'm no longer in Hammerschlag Hall. I'm actually at CIC, Collaborative Innovation Center. And office hours are still the same. And you can always meet me by appointment, especially if you have questions about 740. I understand that that's not very clear in the handout, in the schedule of classes. But anything related to computer architecture or anything, you can always come and visit, certainly by appointment. So, and this is the pictorial depiction of the office change. As architects, we should always think pictorially, right? This is the building you're in right now. And that was the old office, and this is the new office. Hopefully you know your way to CIC. It won't be hard to find me.
Where's that picture taken from?
Oh, that's your exam question. Any guesses? Where's that picture taken from?
Jouppi.
Where? Jouppi. That's good. What building?
Cathedral.
Cathedral, that's right. Cathedral of Learning. Right. Some people used to call Cathedral of Learning Tower of Mordor, which is not a bad thing, actually. We don't? I guess not. That's right. It's a beautiful tower, actually, but it is pretty dark during the night. I don't know why they don't light it up. I know saving energy is good, but there's some beauty to that tower if you light it up as well. Maybe once in a while you can light it up, save some energy, and use it for lighting it up, right? OK, last lecture we covered a lot of prefetching. Well, hopefully you remember. We'll cover more of prefetching in this lecture. And in the second half of the class, we'll jump into multiprocessing, which we've covered partly before, but we'll jump into a more formal treatment of it. And you remember we've covered some hardware prefetchers, next line, stride, and stream. Today, yeah, more prefetching and multiprocessing fundamentals. Let's talk about some advanced prefetching techniques, because this is actually a fun topic. And again, this is a very fundamental concept employed in many different parts, in distributed systems as well. And some of the algorithms that I will describe can be employed in other systems too. So we've talked about stride prefetchers. I'm not going to cover them again. Basically, these detect stride somehow based on instruction program counter or cache block address. They tie the stride to program counter or some region of memory. And based on that, they try to prefetch data. And we've covered all of this. So this is just to jog your memory. And stream buffers was a particular form of stride prefetching where the stride was equal to 1, right? And you actually had these buffers where streams that have stride equals to 1 were streamed into. Data was prefetched into these buffers. This was the last slide we ended up with last time. We talked about prefetcher performance. Usually prefetcher performance is evaluated with 3 metrics: accuracy of the prefetcher, used prefetchers divided by sent prefetchers, coverage of the prefetcher, what fraction of all of the program's misses can a prefetcher actually prefetch, and timeliness of the prefetcher, on-time prefetchers divided by prefetchers that are actually used. You can actually have great accuracy, but no timeliness, right? You always predict the right address, but you predicted on the cycle it's going to be needed. Then that prefetching is not very useful, right? Even though you may be very accurate. Bandwidth consumption is another metric. This is the memory bandwidth consumed with the prefetcher divided by without the prefetcher. And prefetching, if you have idle bus bandwidth, prefetching can utilize that. Cache pollution is another metric. This is the number of extra demands due to prefetch placement in the cache. A prefetch can evict another cache block that could be useful, right? Especially if the prefetcher is going much farther ahead. This is a bit more difficult to quantify. Actually, you can quantify it, but it does affect performance, just like these other metrics. And all of these 3 metrics, accuracy, coverage, and timeliness, also affect how much cache pollution you get. Right? For example, if your accuracy is 0% and your coverage is, well, I guess then your coverage will be 0% also, right? But if your accuracy is 0% and if you're sending lots of prefetches, then you're likely consuming a lot of bandwidth, and likely you're polluting your cache. And we talked about these metrics being against each other, and you can think about that on your own too. So prefetcher aggressiveness is a key configuration parameter of the prefetcher that affects all type of performance metrics. Aggressiveness depends on the prefetcher type, but for most hardware prefetchers, there are 2 things that determine the aggressiveness. One is the distance of the prefetcher, prefetch distance. Basically, this is how far ahead of the demand stream that the prefetcher is going. So this is the last accessed address, let's say, by the processor. The prefetcher's distance is how far ahead from that address is the prefetcher, last prefetched address. And if this distance is large, the prefetcher is aggressive, right? Actually, I have an illustration over there too. And prefetch degree is how many prefetches do you generate per demand access. When a demand access comes from the processor, how many prefetches does the prefetcher generate to go ahead? Let's take a look at this. This is the access stream of the processor. Let's say the processor is accessing X. And this is the predicted stream by the prefetcher. And prefetcher has prefetched all the blocks between X and this P max. And this is the prefetch distance. Prefetch distance can be very conservative. This is a very conservative prefetcher with a small distance. This is a middle-of-the-road prefetcher. And this is a very aggressive prefetcher, which is much farther from the processor's demand stream. And if you look at this very aggressive, this is likely to be less accurate because maybe the processor will stop accessing the stream, right, at this point. And you prefetch lots. Whereas if you're conservative, you prefetch very little. Make sense? And prefetch degree is when the processor accesses X plus 1, how many prefetches are actually generated by the prefetcher. In this case, the prefetch degree is 3. The prefetcher generates P plus 1, P plus 2, P plus 3. Make sense? And if you want to make it very aggressive, maybe you generate 20 prefetches, right? Very conservative, you generate 1 prefetch. OK, how do these metrics interact? If you're very aggressive, then the prefetcher is well ahead of the load access stream of the processor, which means that it can hide memory latency better, right? When the processor needs the address, hopefully that address is already in the cache. And it's more speculative. If the prefetcher is very conservative, then you're closer to the access stream, which may not hide memory access latency completely because of the reason we talked about earlier. But this reduces the potential for cache pollution and bandwidth contention. Right? You're not wasting things. And this also improves your accuracy, probably. Although that's a mixed bag, right? It may not necessarily improve your accuracy because you may be very conservative, but you may be prefetching the wrong thing. Whereas if you prefetched a little bit farther ahead, you would actually get the right thing. OK. So this leads to higher coverage, better timeliness, but likely lower accuracy, higher bandwidth, and cache pollution if you're very aggressive. If you're very conservative, you're likely higher, more accurate, consume less bandwidth, and pollute less. But it's likely lower coverage and less timely. You're not covering as many misses, maybe. OK, let's take a look at the correlation between prefetcher accuracy and performance. This is from the paper that you're assigned, actually, that you're reading, Feedback-Directed Prefetching. I hope you guys are reading that. That's a fun paper. And actually, those kind of techniques are employed in existing processors today, throttling the prefetcher such that it doesn't do the wrong decisions. The paper you're reading is from 2007. X-axis shows the accuracy of the prefetcher across a number of workloads. And the y-axis shows the percentage IPC change over no prefetching at all. If you look at this, there's some correlation, right? If your accuracy is really low here, the IPC change is very low also. So for example, there's a workload that loses 50% IPC performance, which is terrible. You don't want that, right? You're trying to gain performance by prefetching. And if your accuracy is high, that doesn't necessarily always mean that you gain a lot of performance. For example, there's this workload here that has almost 100% prefetch accuracy, but performance improvement gained by prefetching is about maybe 5% or so. Right? Why? Because maybe the coverage is low, right? Maybe you're very accurate, but you're not generating a lot of misses that are actually needed by the program. OK, so this is another depiction of the data here, a more comprehensive one. This is from the paper you're reading again. X-axis shows some spec workloads. Y-axis shows instruction per cycle performance. And 4 bars, no prefetching, very conservative prefetching, middle-of-the-road prefetching, very aggressive prefetching based on the distance and the degree. If you look at this across all these workloads, actually very conservative, very aggressive prefetching provides the best average performance, right? Although it has diminishing returns. And the performance improvement with prefetching is very good. But there are some workloads where aggressive prefetching is bad. Prefetcher being 64 cache blocks ahead of the processor is bad. You lose almost 50% performance in this workload, in AMP, for example. And I encourage you to read the paper, what happens here. Here, there's a streaming prefetcher that's used, but the demand access stream actually accesses every 256 cache blocks. So without a good strike prefetcher, you cannot capture that. OK? So we don't want this part, right? Whenever you design a good technique, a performance improving technique, you want to not only improve average performance, but do not degrade the performance on applications that are already performing well. So how do you do that? The idea is to throttle the prefetcher. It's a simple idea, right? Dynamically monitor the prefetcher performance metrics, at least some of them. Throttle the aggressiveness up or down based on past performance. And the implicit prediction here is that the past performance is a good indicator of future performance, like many things we do in computer architecture, right? Or many things you do in your life too, probably. You have this implicit prediction. And based on this, you could also change the location prefetches that are inserted in the cache based on past performance, right? Because, for example, maybe you figure out that the prefetcher was polluting the cache. In that case, you may want to insert the prefetches to, as we discussed, at a lower priority in the cache. You might want to insert all the prefetches into the LRU position, right, instead of other positions in the cache, such that they don't disturb the demands. That's the idea. Simple. And if you read the paper, you already know that. You could explain this to me too. So this is pictorially how the mechanism works. Basically, the accuracy of the prefetcher is computed. You have high, medium, and quantized into 3 categories, high, medium, or low. And if the prefetcher has high accuracy and it's not late, but it is polluting the cache, then the aggressiveness of the prefetcher is decreased. And you can imagine why these decisions are made, right? Because you're accurate, you're not late, timely, but you're polluting. You're evicting a lot of cache blocks that are going to be used. If you decrease the aggressiveness, the hope is that you will be more timely, maybe. You're not too early, right? If the prefetcher has high accuracy but it's late, then the mechanism increases the aggressiveness. Why does this make sense? Because you have high accuracy, which is good, but the prefetchers are coming late. Demand requests are coming right after the prefetchers are issued. So you would like to give more distance to the prefetcher such that it can be more timely, which happens by increasing the aggressiveness. And you can actually fill this, and you can study this on your own since you're reading the paper anyway. But this is determined. These are heuristics to throttle the prefetcher aggressiveness. These are not necessarily the best heuristics, right? Maybe you can come up with better mechanisms to improve upon these. And what happens once you throttle the prefetcher accordingly to those heuristics? These are the performance results that you can see in the paper also. This was no prefetching, the leftmost bar. Rightmost bar, the second bar is the very aggressive prefetching. And these two provide dynamic insertion into the cache. and dynamic aggressiveness adjustment based on this figure. And this is feedback-directed prefetching, including both. If you look at this, performance improves slightly compared to very aggressive prefetching, but that's average performance. The applications that were suffering very much because of very aggressive prefetching now gain performance compared to no prefetching. So this throttling enables you to gain performance on many applications. And in some applications, you lose a little bit compared to very aggressive prefetching, but you curb the performance loss that you see in these applications. So takeaway, basically, whenever you have a mechanism that tries to improve performance, you would like to throttle it in the right way. You'd like to control it in the best way using its configuration parameters and the metrics you observe at runtime such that you can get the best performance across different workloads. Does that make sense? You could imagine this for other techniques we've discussed also in prefetching. OK, so hopefully you'll enjoy this paper also. And maybe you can develop better mechanisms. Because it turns out whenever you have another actually fundamental thing is whenever you have mechanisms like this where you quantize accuracy and pollution or some metric, the mechanism becomes relatively complicated, right? How do you decide that threshold? If you fix a static threshold, you may run into non-robust decisions. And we've talked about that when we talked about thread cluster memory scheduling in the memory scheduling lecture. OK. So we talked about regular prefetching for regular access patterns. The prefetcher we examined, stride prefetchers, stream prefetchers. They're all for regular access patterns, right? But programs have irregular access patterns as well. And these are a lot harder to prefetch for. That's why these are very interesting problems to examine. So you have indirect array accesses, for example, linked data structures. How do you prefetch for them? Where the addresses may not have predictable or easily predictable relationship with each other. Multiple regular strides. What if your stride is like this? 1, 2, 3, 1, 2, 3, 1, 2, 3. This is if you look at the memory addresses, the distance between memory addresses over time. What about random patterns? Can you prefetch for them? And can you actually have a generalized prefetcher for all patterns? So we'll try to cover some of these. This is a very difficult problem, actually, especially as you go down this list. Random patterns and generalized prefetcher for all patterns becomes a difficult problem. And we'll talk about some of these prefetchers that people have developed to solve these problems. Also, especially focused on 3 prefetchers: correlation-based, content-directed prefetchers, and pre-computation, or execution-based prefetchers. And you've seen one of them, right? You guys remember? A pre-computation-based prefetcher? Run ahead, right? It is a prefetcher. It's a prefetching mechanism that pre-executes the program to actually cover any kind of pattern where it doesn't have limitations on. OK, let's look at correlation-based prefetchers. It's actually fun. Let's take a look at this following history of cache block addresses that the processor accesses: A, B, C, D, CEA, CFF, ... Right? If you look at this, you can actually show this as a Markov model. What is the probability of an address coming after another address? So if you look at this, address B, if you access address A, with 60% probability, the next address you're going to access is address B. Right? You can do that computation because AB, whenever you see A, the next address is B here. The next address is C here. The next address is A here. The next address is B here. The next address is B here. So 3 out of the 5 times you see A, the next address is B. 1 out of the 5 times you see A, the next address is A. And 1 out of the 5 times you see A, I hope I'll find this. OK, there you go. The next address is C. That should be 0.2. So there's some correlation between the addresses you see in the access tree, right? A Markov prefetcher tries to exploit that correlation. It records what address comes after you see one other address. So you can record this Markov model in a table, and you can say, whenever I see A, most likely the next address I'm going to see is B, where A and B may have nothing to do with each other in the space, right, in the memory address space. And when the processor accesses A, the Markov prefetcher looks up its table and says, oh, the next address is likely going to be B, so I better prefetch that. Make sense? And there are some cases here where you have 100% probability, right? After E, you always see A, for example, EA, 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 EA. If you can distinguish these patterns, you can get a prefetcher that is very accurate, hopefully, and that can prefetch more or less random patterns. Well, it's not really random because there is some predictability, obviously, right? But non-striding patterns or non-streaming patterns. Make sense? So that's the idea. So how do you do that? We can talk about this. This is described in this paper, Prefetching using Markov predictors. But why does this work? So I'll give you just a simple example, which is a linked list, right? This is not the same example that I drew over there, but if you have a linked list, and it so happens that it's not changing, you traverse it once, you know that this is the order in which you see the memory addresses, and then the program loops, and you traverse it again. Now you've already recorded, you've seen after A, you see B. After B, you see C. After C, you see D. The next time you traverse this linked list, you actually know what addresses you're going to see if you recorded it. Make sense? So that's why this mechanism can work. And that's the idea. Record the likely next addresses after seeing an address A. And next time A is accessed, we prefetch those likely next addresses, B, C, and D. In this case, A is said to be correlated with B, C, and D. In this case, A is correlated with B. Actually, A is correlated with B, C, and D also, right? Okay. So in this case, I didn't describe this, but basically, you record in a correlation table. This is called a correlation table. What address comes next after an address you're accessing? This is the cache block address you're accessing, and this is the potential addresses that can come next after when you see A in the past. And you can associate confidence with each of those addresses, right? And confidence can be actually the probability that you observed in the past, the next address. So Markov prefetching is actually, it's a nice idea, but it turns out it's not easy to implement, right? Because what if you have a 1,000,000 entry linked list in this case? Do you have a huge table? That's tough, right? So people have tried to reduce the cost of this quite a bit. And reduced cost versions have been considered for implementation. But I'll let you read those papers. You can certainly talk with me about that. Another issue here is prefetch accuracy is generally low if you just, for example, if you just correlate A and B. After A, you store just B. When the processor accesses A, you need to, if the prefetcher prefetches B, it may be too late. Right? So usually, such prefetchers correlate an address with many later addresses. So you can prefetch n addresses ahead. Right? And prefetch accuracy can also be improved by using multiple addresses as keys. Right? For example, if you've seen A and B in sequence, then the next address is likely C. In this case, A and B in sequence are correlated with C. So you can imagine different ways of doing this. So this becomes harder, of course. This is a nice linked list. I give you a nice example where this works. But what if you have a tree, right? Now, if you have A, B, C, this is your binary tree. The way in which you traverse this binary tree determines what address comes next after you see one address. So if you traverse it this way, let's say, because branches go this way, because you're comparing some data that happens to take you this way in the tree, what you see is A, B, C, right? If the data that you're accessing, let's say you're searching a word in this dictionary that's organized as a binary tree, and the traversal takes you to these nodes, what you're accessing is A, C, F. Right? So the next addresses you see after A are B and C here. B and D here. And the next addresses you see after A are C and F here. And they have nothing to do with each other. Right? So you can actually get not so improved accuracy. So maybe correlating A and B together is a better idea. Right? That way you can get better accuracy. After you see A and B, you'll see D. Make sense? OK. So you can think of this on your own. Any questions? You can think of what kind of accesses actually this can cover. Well, I guess the advantage is it can cover arbitrary access patterns. It can cover linked data structures, like this, what I've shown. It can actually cover streaming patterns, too. It's actually simple. Streaming pattern is, or striding pattern. Let's say you're seeing A plus 4, A plus 8, A plus 16. What did I do? No, A plus 12, A plus 16. Here your stride is 4. Right? A stride prefetcher could nicely detect this. If you have a Markov prefetcher, it can also detect this, right? Basically, in the correlation table, what it would record is, after A is seen, the next address is A plus 4. If the previous address is A plus 4, the next address is A plus 8. If the previous address is A plus 8, the next address is A plus 12, and dot, dot, dot. And this is the previous address. This is the next address. So if you look at this, you can actually prefetch for this streaming or striding pattern. But it's very inefficient, right? Because you need to store every entry in the streaming pattern in the correlation table. Whereas a stride prefetcher is very efficient. It just says, in this memory region, my stride is 4. You record the last stride as well as the last address accessed, and maybe a confidence. And that's it. Yes?
You combine it and make a tournament prefetcher.
You could, actually. You could have hybrid prefetchers. That's true. If you can somehow detect where you're being better. And maybe some of the metrics that you observe for each prefetcher can be decided to you choose the prefetching algorithm dynamically. OK. What are the disadvantages of this? Can anyone think of the disadvantage of a Markov prefetcher? Yeah, one in hand, probably. No? It's perfect. It covers everything. Takes time to warm up. That's right. So another way of putting this is, well, I guess I have it here. I should have done this in a different order. Basically, it cannot reduce compulsory miss. It needs to see addresses to be able to prefetch for them. Whereas if you look at this pattern, a stride prefetcher doesn't need to see all of the addresses. Whereas a Markov prefetcher here, it needs to see all of the stream first so that it can populate this correlation table. Right? So it cannot reduce compulsory misses. You have to see those addresses at least once. And there are a bunch of other disadvantages, actually. One big one that we briefly discussed is this correlation table needs to be very large for high coverage. If your linked list doesn't fit in your correlation table, too bad, right? Maybe you won't get the prefetches. And low time, it also has low timeless because lookahead is limited since a prefetch for the next access is initiated right after the previous one. But we already discussed how to get around that, right? Whenever you have low timeliness, you try to prefetch ahead. Right? Not correlate A with only one address, but correlate A with many different addresses. Or correlate A with a farther ahead address, right? Remember we've discussed jump pointers in the last lecture, skip lists. You don't only have pointers to the next node, but you also have pointers to the nth next node. So that way you can do that correlation. And this also actually consumes a lot of memory bandwidth because if you want to have high coverage, if you want to have high coverage here, you would like to probably record B and C as the next addresses after A and prefetch both of them. Because here you don't know where you will go, right? And that leads to higher memory bandwidth consumption if you want to have high coverage. Make sense? OK. You can actually think about a lot of different ways of optimizing this. And people have done that a lot in the past decade or 15 years or so. OK. So this is actually a very high-cost method of trying to prefetch for these linked data structures. can you have a lower cost method for prefetching for these linked data structures? And we'll cover that next. And that's the idea of content-directed prefetching. It's actually somewhat related to your exam question, and we covered this earlier with address value delta prediction, a little aspect of it. The idea here is very simple. It's a specialized prefetcher for pointer values. Whenever you bring in a cache line, cache block, search the cache block for possible pointers and issue prefetch addresses for them. Simple. There's no need to memorize or record past addresses now. You don't need a huge correlation table like this, even though this is not for pointers, maybe. Oh, that's not us. OK, I guess I give up. We don't have the pointers here. You don't need to memorize the past addresses. And this can eliminate compulsory misses also, because the cache block may have pointers that you've never seen before. And I'll give you an example of this, actually. The downside is it indiscriminately prefetches all pointers in a cache block, and we'll talk about a way of fixing this, or at least a general method of fixing this. So how do you identify pointer addresses? We've already talked about this before. Remember, this was also your exam question, one of the questions in the potpourri. Well, you can compare the address-sized values within cache block with the cache block's address. Although the exam question was a little bit harder than that, and we can go over that later on. But basically, this is your cache block, and it has a bunch of values. And this is the address of the cache block. Let's say address A. You compare each of the values in the cache block with that address, and you compare the top bits of each of those values with the top bits of your address. And if there's a match, that means that it's likely a pointer. Why? Pointers are from the same memory space, right? Same region of memory. OK, let me give you a full example of this. Pointers are virtual addresses, and that was the trick in your question, actually. A pointer in a program is a virtual address, right? You cannot compare a physical address. So you have a virtual address predictor. Let's say you're accessing this cache block at this address, and the cache block is brought to L2. Well, actually, cache block is fetched from DRAM and brought to L2, and this is what you get in your cache block. And let's say you have a bunch of values in your cache block, and this is the address you're accessing. You have comparators for each pointer-sized values in your cache block, and you hopefully compare the most significant bits of the virtual cache block address to the most significant bits of the pointer-sized values in your cache block. And in this case, only one of them match. And you generate a prefetch for that address that matches. In this case, the comparison is to the top 12 bits, saying that this region of memory that has bottom 20 bits are likely to be allocated for the same from the heap space or pointer space. Make sense? OK, so this is actually fun, right? This is a pretty cool idea, because now you don't need any space at all to store any address. You're using the cache block, which you're already storing in your cache, to predict the addresses. Now, the downside is it may be that you may have many such pointers, right, that match. But you may not need all of them. So we're going to try to fix that problem. So the problem is hardware does not have enough information on pointers, but software does. It can profile to get more information. So why don't we have the compiler somehow do program analysis? Oh, OK. Go ahead.
So if we use virtual address to prefetch, then don't we also have to keep a track of which process or what generated the virtual address? Because it can be different for different programs.
So you need to access the TLB.
Yeah, but even within the TLB, you have to know which. So we're down in the L2 cache, right? And then we have this virtual address that can be a virtual address.
That's right.
But that virtual address can exist in many memory spaces, right?
Oh, you need to know which program to do. Yes. So that's a good question. You're thinking well. You need to have somehow the thread ID associated with the request and index the right place. OK. it is actually kept track of today. But you can't make it work, basically, because this is all speculative, right? This is not for correctness purposes. You're just speculatively generating a request. Even if you don't have the thread ID, it'll generate a request for you. Maybe it's not going to be useful. The hope is that two virtual addresses will not match in a program, in two programs. What's the likelihood of that happening, right? You're accessing with a virtual address a cache line, and you have another virtual address from some other program in that cache line. Probably not. OK, so yeah, we don't want to prefetch all the pointer values that we see. So we want the software to provide hints as to what to prefetch. Right? And actually, the software can do this better. And I'm not going to discuss this in detail. If you're interested, you can look at this paper. But the idea is somehow which pointer addresses are likely useful to prefetch are hinted by the compiler. And the hardware uses these hints to prefetch only those likely useful pointers. If the compiler actually tells the hardware what addresses are pointers, the hardware, and what addresses are likely useful pointers, the hardware can do a better job in prefetching the linked list, for example. Let's take a look at an example. This is actually a hash table lookup, the linked list traversal in the hash table lookup function from a minimum spanning tree program, which computes the minimum spanning tree. And this is basically a simple hash table lookup. You provide a key, and that key is bucketed, and you search for that key in a linked list that is within that bucket, hash table bucket. And I think I have an example of this. Yes. So this is what your hash table kind of looks like. For each bucket, you have a bunch of keys that are in the linked list, different keys. And this is another bucket. And within the key, you have, within this node structure, you have two pointers to the data that you want to do something about. In this case, when you search for a key, it's very likely that that key is going to match only one keys, right? Only one of the keys in the linked list. Which means that it's very likely that you're going to traverse through this linked list. But it's very unlikely that you're going to touch these pointers, the data pointers. You're going to touch those data pointers only for the node whose key matches the input key. But if you look at a content-directed prefetcher, let's take a look at the layout of one of these linked lists in the cache block. Let's say you've accessed this cache block here, this bucket here. And this is the layout in the cache block of these nodes. You have the key. You have the pointer to data 1. You have the pointer to data 2. And you have the pointer to the next node. And then for this, you have the key. You have the pointer to the data 1, pointer to data 2. And you have the pointer to the next node. If you look at a content-directed prefetcher, it will actually generate requests for all of these pointers, assuming it's identified correctly. The pointers are identified correctly. Whereas it's very unlikely that the data in pointed to by D1 and D2 will be accessed. Only one node can match. At most, one node can match, actually. Maybe the key you're searching for doesn't exist, right? In that case, you don't have any matching node. But you know that you actually need the next one, or very likely need the next one. Again, because at most, one node will match. Right? You will very likely traverse that linked list. In fact, you can probably calculate the probability of traversing the number of linked list elements you're going to touch, given a uniform distribution of keys. Right? So the idea is basically software knows this information very well. Right? In fact, the programmer can hint this information, or software can profile, even if it cannot do program analysis. And the software tells the hardware, it's very unlikely that these D1 pointers are going to be used, but it's very likely that these next pointers are going to be used because you're likely going to traverse to the next node. So prefetch only these next pointers. And how do you do that? With a load instruction that does this traversal, you can actually have a mask saying, these are the pointers, these are the locations of the pointers in the cache line you bring in that are likely to be useful. And that's what the paper talks about. But that's the idea. And And if you do this, now only the next pointers are prefetched. And for some reason, this is not highlighted here because we're looking at this. So whenever you access this node, you prefetch this next pointer and not prefetch the data pointers. Make sense? OK. So you can actually make a lot of the prefetching mechanisms more efficient if you provide more information from the software. So the downside of this mechanism is obviously somehow somebody needs to provide this information, right? So there's more burden on the software to provide this information to make this more efficient. OK. Let's take a look at, before we take a break and start the next part of the lecture, let's take a look at execution-based prefetchers also. I briefly given you the idea, so I'll go relatively fast here. The idea is pre-execute a piece of the program solely for prefetching data. And you only need to distill pieces that lead to cache misses in this case, that enables that distilled piece to go far ahead than the program. This is also called a speculative thread. You can consider the pre-executed program piece as a thread, right? And we've talked about this. Run-ahead execution can be considered a separate thread, even though it's not software visible. Some of these ideas that we will describe are actually going to be software visible. The programmer will create the speculative thread. The speculative thread can be executed on a separate processor or core, if you have that, on a separate hardware thread context, if you have fine-grained multi-threading, or on the same context in idle cycles, like run-ahead execution does. So there are several key issues in these execution-based prefetchers. First, how do you construct the speculative thread? So if you actually construct such a speculative thread, now you can cover any arbitrary cache miss, right? Now you're not bound by patterns in your program or pointer addresses that you may find. Now you're really executing the program to get to the next cache miss. But how do you construct it? You could actually do it in software, hardware, or use the original program, just like run-ahead. And we'll talk about a software-based mechanism. In general, doing this in hardware is relatively difficult, especially if you want to prune the program, right? Because you need to find what instructions do you need to execute to get to a load instruction. You could do it in hardware. There have been proposals, and those are usually costly. Well, run-ahead execution is a specialized way of doing it. So what do you want from the speculative thread? First, you would like it to discover misses before the main program does, right? Which means that it should execute much less than the main program. So to get ahead, the speculative thread can execute only those only those instructions that lead to address generation computation, and maybe branch resolution, right? And it can use value prediction to predict unknown values, right? Because you would like to execute the speculative thread, but you don't know what are the input values, because you would like to prefetch for a later load. Maybe you predict those input values such that the speculative thread can execute fast. So this is a pictorial depiction of this. This is thread-based pre-execution. This is actually employed in processors. You can do that. And I'll show you a paper that actually evaluates it. The idea is, let's take a look at this load. You could do this for branches also, but I'll focus on the load. Here's this load in the main program that usually causes cache misses. We could insert a speculative thread that is forked off the main program at this point. When the main program reaches this point, there's a fork to the speculative thread. The idea of the speculative thread is to execute a distilled portion of what happens here in the main program to compute the address of the load much earlier than the main program reaches this load. In this case, the speculative thread executes. It reaches the load. It generates the cache miss. That cache miss is handled here. And by the time this main program actually reaches the same load, this cache miss is already serviced and placed into the cache. So this load incurs a cache hit. That's the idea. You could do it for branches as well. And if you're interested in that, you could read some of these papers. Basically, the idea is the same. By the time the branch is actually fetched, you execute a speculative thread that computes the condition of the branch or the direction of the branch. And when the branch is fetched, you feed that pre-computed branch direction to the branch predictor so that you go the right way. If you have enough hardware context, you could do that for hard-to-predict branches and cache-missing loads. That way, you can get a speed up. This is called thread-based pre-execution, speculative threading, or helper threading in general. Helper threads are a common term. OK, let's take a there are several issues in this, and I'm not going to go over this in detail. You can think about the upsides and downsides. First, where do you execute the pre-computation thread? You could do it in a separate core. In this case, the speculative thread doesn't contend with the main thread that much, right? Or a separate thread context in the same core, now you have more contention, just like fine-grained multithreading that we've discussed. Or same core, same context when the main thread is stalled. This is like run-ahead execution. But it doesn't have to be run-ahead execution, right? Whenever the main thread is stalled, you context switch to this speculative thread. And if your context switch is very fast, you could do that very quickly. In a sense, run-ahead execution does a very fast context switch to a speculative version of the same program. But you could context switch to this other thread. When do you spawn the pre-computation thread? Where should this fork point be? And that's a difficult question, actually. If you, because this determines your prefetch distance, if you will. You can insert spawn instructions well before the problem load. If you actually do that too early, if you put the fork point of the thread too early, then you may actually never get to this load, right? Because there may be branches in between. And if you put it too late, you may not actually cover that latency. By the time this load is executed, this speculative thread is still going. You don't want that also. So you need to orchestrate this well. Or you could actually spawn the pre-computation thread when the main thread is stalled. But that leads to another set of trade-offs, right? Which means that you may not actually cover that entire latency of the load. You may not even actually finish the speculative thread, right? While the main thread is stalled. And finally, when do you terminate the pre-computation thread? I'll describe briefly a paper that talks about pre-inserting cancel instructions. Because if the pre-computation thread is still going on, even though the load is executed, you don't want that, right? Or if you figure out that the pre-computation thread is not doing useful work, you want to cancel that somehow. And that's the second thing that I just described is basically based on effectiveness and contention feedback. So you have a large design space in this kind of work. And you could actually experiment with this in your machines today. OK, so and this is a paper actually that talks about how to take advantage of a multi-threading processor, a simultaneous multi-threading one. The idea in simultaneous multi-threading is you can actually execute from multiple threads in the same cycle. You have enough functional units, and multiple threads can be dispatching instructions in the same cycle. It's very similar to fine-grained multi-threading, except now the dispatch is in fine-grained multi-threading, you have only one thread that you're fetching from and executing from in a given cycle, right? Different threads are in different pipeline stages, but only one thread is actually issuing instructions into the execution units. In simultaneous multi-threading, it's even more fine-grained. You have multiple functional units, and one thread can be sending an add to one adder, another thread can be sending an add to another adder. We're not going to cover this in this course. We're going to cover it in 740, and there are a lot of design trade-offs. This is what Intel calls hyper-threading, actually. Hyper-threading is one version of simultaneous multi-threading. And this, I believe these are actually evaluated on something like an Intel processor. But basically, you can use software-based pre-execution for different kinds of access patterns. While the main program is being executed on one thread context in a processor, pre-execution threads can be executed on other thread contexts. And when can this help? For example, if the main program needs to traverse through different pointer chains. Actually, this is an easier one to understand. Let's say this is your main program. It needs to go through a bunch of function calls. Foo, bar, baz, and cux. I don't know what that is. I guess I don't know beyond foo and bar. Those are two things that everyone uses, right? But you could design a program that speculatively pre-executes these future functions. So when the program is executing, main program is executing foo, there's a speculative thread that's executing bar, just for prefetching purposes. There's another speculative thread that's executing baz, just for prefetching purposes. Another one that's executing cos, just for prefetching purposes. When the main program is traversing one of the pointer chains in a hash table bucket, let's say you're actually, well, this is the hash table that I drew here. you're actually searching for many different keys. Key 1, key 2, key 3, dot, 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 as inputs to the main program. While the main program is traversing the linked list in the bucket that key 1 maps to in the hash table, while this linked list is being traversed, the speculative thread can actually traverse the linked list in the bucket where this key 2 maps to. It can speculatively do this linked list traversal such that this linked list is prefetched into the cache while the main program is working on this linked list. And if you want to get farther ahead, you could actually have a speculative thread working on the next key, working on the next key, right? That's the idea. So it's beautiful, right? You can overlap lots of latency, and you could prefetch arbitrary patterns. Because these keys, these buckets, the location of these buckets and the linked lists may have no predictability if you just look at the addresses. But now you're really speculatively executing the program. And there are other examples here that you can look at. So I'm not going to go over this, but and I didn't assign this as a required reading, but this is a beautiful description of how to do speculative prefetching for a workload called MCF. MCF is a workload that actually traverses a bunch of linked lists. It does vehicle scheduling for a bus depot. I don't know if that's interesting, but people actually write programs for all sorts of purposes, right? And what it does is, it does pretty much something like this, basically. You traverse one linked list based on one of the keys, inputs, and that's this for loop, basically. For each trip, basically, I assume what it does is you actually, given a trip, you try to find a vehicle that matches that route. And for each trip, you try to do this vehicle, let's say. I'm just making it up, but that's the idea. Your key is the trip ID, and for each key, you traverse a linked list. Now, you can transform this program such that you have a pre-execute start instruction. In this case, we have a pre-execute start instruction, and this for loop goes through these different keys. And you have a while loop in between, which basically does this linked list traversal. So while loop does one linked list traversal, one iteration of the for loop, let's say. If we want to prefetch for the next iteration while we're doing this current iteration, before we go into this while loop, before we go into this linked list traversal, we insert a pre-execute start instruction starting from end of the for loop, which basically spawns a thread that's starting from here, which you increment the iteration count such that you go to the next key. Now, the thread executes here, it goes into the while loop. But it also has a pre-execute start. So while you're executing the speculative thread, you can actually spawn another speculative thread, right? So you can keep going on in the future. Does that make sense? So it's a lot of fun. And at the end, here, you can have a pre-execute stop instruction. Right? So in this case, I guess pre-execute stop ensures that you don't go too far ahead. You stop the thread that's pre-executing. And if you actually come to the end of the keys, you have a pre-execute stop instruction here also. OK? So I'll let you actually read this. This is actually a lot of fun to read. So what do you need for this? The support is actually relatively simple. You need a pre-execute start instruction, which requests an idle context that starts at the start PC. And you can actually have a parameter that says, whenever this thread executes maximum number of instructions, stop this thread. And the hardware needs to provide support for that. And there's a pre-execute stop instruction that terminates the thread. And you can actually have a pre-execute cancel instruction where you can terminate the pre-execution thread with the thread ID. And somebody can actually program this, right? Once you have these instructions or primitives that are provided to you as a programmer, you could actually do the prefetching yourself. Or the compiler can do this. The hardware can do this also, but now you need to think about how to construct the threads, or how to actually understand the structure of this program. So what is the benefit of this? This paper actually reports significant benefits. In MCF, this program that we've discussed, you get 8% performance improvement. But there are other performance improvements. The minimum spanning tree program that we've looked at earlier, that actually does a lot of linked list traversals also, it gets about 36% performance benefit. But if you're interested, you can read the paper, or you can actually do this kind of programming yourself, maybe. And there are actually cases, if you look at this, where performance degrades. This is a compression algorithm. Performance degrades by 5%. So maybe pre-execution thread is actually contending with the main thread in that case. There may be many reasons, right? Okay? Or the pre-execution thread may be generating useless prefetches. Okay. So you could actually do this thread-based pre-execution for any kind of problem instruction if you can somehow have the hardware support for it. So in this case, there's a program, another program. This is VPR, which does place and route, placement and routing in a circuit. And this is one hot portion of that program. And you're inserting something to a heap in this case. And it turns out you're doing some comparisons that lead to branch mispredictions and cache misses. So you could actually identify what to execute in a pre-execution thread if you want to prefetch for this cache miss and if you want to pre-compute the branch condition. So how do you do that? I'll give you just one example very quickly. You don't need to know this in detail. First of all, you need to somehow identify a fork point. That's the first step in constructing a pre-execution thread. Where do I fork this thread? And once you identify the fork point, for example, in this case, this is the function that's adding to a heap. And there's this add to heap function. And this is actually encapsulated by some other function. You could decide to pre-execute the thread that tries to prefetch for this cache miss within this function in an outer function, right? Actually, you should probably do that so that the pre-execution thread can get ahead. And let's assume that that's the fork point. Now, how do you actually figure out what instructions should be executed to get to this cache miss? And this is one example from the paper that I mentioned here. And you don't need to know this paper. But the idea is this is the main program. And this is the instruction that caused a lot of cache misses. And how does the compiler determine that? Again, profiling, right? The compiler basically looks at the backward slice of this load instruction that caused a lot of cache misses. What is the backward slice? All of the instructions that lead to the address generation of that load. And the compiler can do that, right? Compiler can do a data flow analysis, backward data flow analysis to figure out what are the instructions that produce the address of this load. And it turns out this is the slice. These are the instructions that are needed to execute this load that happens to miss a lot in the cache. It also actually, this is the hard to predict branch. These are also the instructions that are needed to execute, pre-execute this hard to predict branch. It's much smaller. If you look at this, this is 1, 2, 3, 4, 5, 6, 7, maybe 8 instructions, right? Whereas if you look at this, this is probably around 20 instructions. So that's how the pre-execution thread can go further ahead. Two ways. You prune the thread. And the second way is you insert the fork point much earlier. And if some values are not available when you start the thread, well, you can predict those values. OK. And you've seen run-at execution also. This is the so you can see what is involved in pre-executing a thread and constructing a thread. It actually needs a lot of work. Doing it purely in hardware is difficult. Run-at execution is one way of covering cache misses without actually constructing that thread. Basically, you're using the main program to pre-execute instructions that generate cache misses. And you've seen this before, so I'm not going to cover that. Any questions on pre-execution, thread-based pre-execution? Now you're going to all go and try it and make it work? Yes?
What if you make a tiny core that runs in parallel with the normal core, and it runs on the same PC, so that you don't have to create a separate thread for it? And all it does is to just try to find branches that load and store around like 100 cycles in front of the normal execution.
Well, I like that idea, actually. People have proposed similar ideas where one core prefetches for the other, and the core is actually optimized for just for prefetching. If you can ensure that that core can go ahead faster, then sure, that might work. So of course now you run into trade-offs, right? What is that core can be used for other programs also. And how do you construct that core? But the general idea is slipstream processing. And the idea is you have, or two hands are better than one, right? You have two cores. They both execute the same program. And one of them gets ahead because it does run ahead, for example, even though it wasn't proposed this way. But it basically has a way of getting ahead of the main program. This is the speculative program. And this is the main program, or non-speculative program, let's say. This core executes instructions such that it goes far ahead and provides results in the data cache. And this core can actually use those to execute the program faster. Right? I think that's the idea you're proposing. And this can have advantages. Now we have one core going much farther ahead. It can provide the results to the main program such that this can go far ahead also. Does that make sense? We'll not cover this. Again, this is a topic for 740 and 742. But if you're interested in that, this is a very interesting direction that people are pursuing, especially when you have multiple cores and when some of the cores are idle. Right? And today we have multi-core processors. And if you really care about the performance of a single thread, and you cannot improve it because you cannot parallelize it, this is one way of automatically parallelizing it. One core speculatively prefetching data as well as branch directions for another core. Okay? And the name slipstream, does anybody know where the name slipstream comes from? It's actually an analogy. In NASCAR races, when you're actually racing cars at very high speeds, you would like to go closer. The two cars usually go close. You've probably seen some races, or in Formula 1 also. The cars go very close to each other, right? Because if they're close to each other, they reduce their drift. And both cars speed up because they go close to each other. And that's called slipstreaming in that particular context. Now you're doing slipstreaming in the context of cores. One core is reducing the drift for the other core. And actually, the back core is also reducing the drift for the other core, but we can discuss that if you take 740. Any other questions? OK, I guess let's take a break for 3 minutes, and then we'll start on multiprocessing.